Hello and welcome back. It's great to have you on this channel. I'm Nilesh, and this final video on the Bayesian decision theory series. Now, moving on to general statistical pattern classifier or a Bayes classifier. We have seen a similar image when we talked about perceptron, where we just have this input layer of X and then output layer. In this case, we have this box in the middle, which is the hidden layer, and the nodes in those denote this g1 of x, g2 of x, and gc of x. Those are the discriminant functions, and we could have other layers in here as well. So those discriminant functions are what are the kind of the background for the linear discriminant analysis that in future videos. So let's look at what these discriminant functions are and how they work. So on this figure, just to explain how what this shows is that we have these input values, and each of those values are connected to each of the nodes in the hidden layer, shown by the arrow dots and arrow lines, sorry, orange arrows. And these dotted lines suggest that there could be more nodes here that also connect to these nodes in here. And then for output, the output of these is used to take an action alpha to classify that sample to a particular class. And so that's the output layer. As we can see here, the sample can be classified as it belongs to class omega I if the value for the discriminant function gi of x is greater than gj of x, or when j and I are not equal. And this follows from this relation shown below, which can be derived, which says the first one says that the if for the value of the discriminant function gi of x to be higher or maximum, what we need is the risk associated to be minimum. So the conditional risk are for action alpha I given x should be as low as possible, and therefore the negative sign. They're inversely related. At the same time, we can have the discriminant function value of gi of x uh, equal to posterior probability omega I given x. So, so what we want to do is maximize the posterior probability to get the maximum value for the discriminant function g. And so here for the multi-category case, multi-category in the sense multiple classes, classes from 1 to c, we can, this is the Bayes equation where this is the posterior probability, we have the likelihood prior, and this is the evidence down below. So what we can do is, if we ignore the denominator part here, and if we just consider the top part, the numerator part, and we can use that as well to get the value for the discriminant function gi of x as shown here. And if you take the logarithmic, we can also take the logarithmic value of this, so that's shown by the relation below it. And based on those, then we can have these final relations for the discriminant function g of x. The first one is that it is equal to the difference between g1 of x and g2 of x. The second is the difference between the posterior probabilities. Then we have the added values of this, the likelihood ratio, log of likelihood ratio, and then we have the ratio of the posterior ratio of the prior probabilities. And the values computed for g of x from either of these, if they are positive, if they are greater than 0, then we would classify that sample or data point as belonging to class omega 1. Else, if it's negative value, then it would belong to class omega 2. Now let's look at a different topic. So expected value. If you are familiar with this, you can skip this slide. Otherwise, hang on and we'll look at what expected value is. Again, back to the food processing plant. We have turnips and carrots coming down the conveyor belt. We are taking pictures, and let's say we are doing the counts, how many carrots would be there in the pictures, and using those we can calculate the estimated value of how many vegetables would there be in the image. So to the method to do that would be we multiply this probability by this count value, and so it's like a weighted sum. And so we multiply these 0.01 into uh, 001 into 0, then this into 1, and so on, and so we get the expected value of 3.035. And what that tells us is that on the conveyor belt, with based on the information that we have, we could expect there would be on an average about 3 vegetables in each image, and we'll use that information of expected value in coming discussion. So a normal density expected value is given by this relation where epsilon of f of x is equivalent to the integral minus infinity to alpha, or the product of f of x into probability of x. And again, this could be thought of as how many vegetables were there in the image, and this could be thought of as the uh, probability associated. Or because this is we are integrating it, so this could be maybe the some continuous value, and here we have the count value. So this could be the numbers represented by probability mass function here, whereas we have the probability density function above. Now, moving on, let's look at univariate density. And this is the familiar equation for Gaussian density that can be represented by this notation shown here in orange. So when you see this notation, what it actually means is the P of X relation that's shown here. And in this, we can use this to calculate the expected value. We can use this probability density and multiply it with the values of x to arrive at the uh, average value for the x's. So expected value of x. Can also similarly get the expected value for variance by multiplying the same density with the square differences between the value of x and the mean of x. And here we have uh, a bell curve, which is the normal distribution, and points to read on this is the magenta colored regions are the regions that represent 2.5% of area under the plot, and the rest within middle is the 95% area. So the 95% area is 2 standard deviations away from the mean that's here in the center. So this is mu, so mu plus 1 standard deviation, and then mu plus 2 standard deviation up to here. And then again we go back here, so mu minus 1 standard deviation and mu minus 2 standard deviation. So this total area from this line up to this line, all this area, that would be 95%. Then the point up top that has the highest value for P of x is given by this relation. So P of mu is 1 divided by sigma standard deviation, the square root of 2 pi. And the entropy or the uncertainty is again given by this relation minus integral of P of x into log of P of x dx. And so this relation what we have seen here is for the Gaussian sigma into square root of 2 pi. So here what we are now using is the multivariate normal density, and the bold uh, symbols here denote that those are matrices. And so here we have the value for p of x is given by this relation here, where in the d represents the number of dimensions and the sigma represents the covariance matrix, capital sigma, with dimensions d by d, so d rows, d columns, and these straight lines surrounding the sigma value is saying that that's a determinant. And then up here on the right hand side, in the exponential term, we have this long term which is the Mahalanobis distance, and we'll explain that in one of the future slides. But briefly, what you probably already know what the Euclidean distance is the direct measure of the distance between 2 points. The Mahalanobis distance takes into account the variation in the data to calculate the distance. So that is calculated by this particular equation here, where we have this covariance matrix, uh, inverse covariance matrix in this particular product. And x is the feature vector, mu is the mean vector, and this t denotes the transpose for this term here. Now, this particular expression can be represented in a notation shown here in a dark orange below, n of mu or bold mu on bold sigma, capital sigma. So with that, we can again calculate the expected values for the average and expected of x using this relation integral of x into p of x. Again, we are simply multiplying the value of x with the density, and again here we are calculating the variance, expected variance, and then here we multiply this value, which is the uh, product product of x minus mu, and then multiplying it by density. And this is in a matrix form. In the single form, it would be represented as shown here with x of I, and again the variance would be for ij, this would be x of I minus u mu I into x of j minus mu of j. Now uh, how those uh, distributions can be transformed in linear features, can be transformed in feature space. So here this first example where we have this distribution given by this particular relation notation that we have seen before, and this is a contour plot with a centroid in the center denoted by mu, so that's the mean. And if we project that on this line a, p is for projection there, we get this distribution which is now denoted by mu of sigma squared. So that's the normal bell-shaped curve that we see, where the feature space is x1 and x2 on the x and y axis. Another way to transform is in this way. We can transform this particular distribution to what we have here, which is A transpose mu and A transpose sigma A, and that's what this would look like. Furthermore, we can do another transformation that's shown here, where all the points, they are now uh, of the same variance. So we have this identity matrix here for variance, and so this is also an example of whitening or spearing. We have uh, done a video on this as well in this series. Want to check that out. Now, the Mahalanobis distance is given by this relation shown here. So what that tells us is that for let's say we have a cloud of data points here, and these contour plots represent the Gaussian density. So the Gaussian density on anywhere on this plot would be the same. What Mahalanobis distance does is that it uh, it includes the variation in the data when calculating the distance, because we are multiplying by the covariance matrix, and that measure is used to find proximity of points from the centroid shown here by the black dot mu. And I've also added these relations for the volume of hyperellipsoid and hyperspheres, uh, just for information. Now, the discriminant functions, we have seen some examples earlier. So here we have the discriminant function for normal density, and the relation is given here, which is natural log of p conditional probability plus log of the prior values. We have seen this first part earlier. Now, this conditional probability here, the likelihood, can be represented by this particular distribution, which is again in turn given by this formula down below, and that can be used to compute this large relation that's shown here in the magenta outlined box, and that is what we'll use in the coming up slides to uh, see how we can get the discriminant function values. So the first term here, which is this, the sorry, this term here, that as you can see, it's the Mahalanobis distance, which is what we saw earlier. And then we have two log, and then the rest are logarithmic terms. This is 2 pi. This is the covariance matrix, and this uses the prior. Sorry, yes, that's the log of priors. The very first case that we are going to look at is when the covariance matrix is diagonal. So uh, what I mean by that only the diagonal elements have non-zero values, and off diagonal elements are all zeros. Because when we multiply the variance with I, that is the identity matrix, it only has the diagonal elements as 1, others are 0. Now, the very first case, because we are considering a diagonal covariance matrix, these two terms can be ignored. And based on the remaining terms, we can write this relation for gi of x, which is equal to the norm of x minus mu I and divided by 2 sigma square plus this term right here. So uh, what we have in this particular part is shown right here on the right hand side, because this was a diagonal matrix. And then that can be used to derive this equation, which is the relation for the linear discriminant. Gi of x is equal to w I transpose x plus wi0, where this wi0 term is the bias term given by this relation, and the wi is given by this relation, which is 1 divided by sigma squared mu of I. And now using that relation for the normal density, what we have here is the W transpose into x minus x0 is equal to 0. So these are the decision surfaces, uh, or we are trying to find the decision surfaces for hyperplanes, and w is given as omega I mu I minus mu j. The hyperplane through point x0 on here, and orthogonal to the vector w, this one is given by this relation down below. And to visualize that, let's look at this particular relation here. So if we assume that the probability for the class w omega I and omega j is the same, the prior probability, then these term can be ignored, and what we have left is just this part, which is just middle, or trying to find the middle point between these two means. And so if we have these two curves, the um, point is shown here by the dotted line. So we have the priors as 0.5, 0.5, then that's where the decision boundary would be. So this is the space R1 for carrots, this is the space R1 for turnips. We now can see that if the priors are not the same, then the decision boundary could be shifted. So let's say if the prior for class omega 1 is 0.7 and class omega 2 is 0.3, then the decision boundary would shift toward the right. If we have a even higher probability of class omega 1, say to 0.9, then we are much farther away on the right hand side on this particular plot. And the implications of that are that we now would be wrongly classifying lot of turnips as carrots, and the same would happen here, but then here we are completely off when we are doing the classification, and so the error rates again would be much higher. This is another example now in 3D space. I'll encourage you to look at the images in chapter 2. They have really nice images. I've tried to uh, create some examples here, but if you want to look into this further, I definitely want to check that out. So here we have the sphere, uh, two spheres separated by this plane. The point to note here is that the plane is, uh, at least I was trying to draw it perpendicular to the line that joins the centroids of these two spheres. So the plane is perpendicular, orthogonal. And as we increase the value of priors, we start out with the prior of 0.5 for both, then we increase the prior for caret to 0.7. So the plane moves towards that side, and then we start classifying some turnips as carrots, and if we move further, then we have a whole bunch of turnips misclassified as carrots. The second case we're going to look at is where the covariance matrix is not diagonal, but all the classes have the same covariance matrix. So sigma I is equal to sigma. And so again, in this case, we can ignore these two terms, and based on that we arrive at this term. Remember, in previous case, this inverse of the sigma matrix was not there because it was diagonal. In this case it is there, and based on that we arrive at this linear discriminant relation, w transpose t and w I transpose x plus w I omega, and it is given by this relation, and the wi is given by this relation which has inverse of covariance matrix. Now again, with the same setup with the covariance matrix, or the classes are same, we arrive at this relation for the hyperplane x0, and this can then be used again to uh, classify the data points. Here is an example where showing the same hyperspheres. We have the carrot and turnip. However, one difference in this plot as compared to the previous plot that we saw is that the hyperplane is no longer orthogonal to the line that joins the mean of these two spheres. It is at an angle. Again, if we increase the value of priors, we see that we can shift the decision plane to either of the sides based on which prior we are increasing. Finally, let's look at a situation where the covariance matrices are different for all the classes. And in this case, then we can only ignore this term. All other terms stay. And this is the relation that we get for the quadratic discriminant gi of x, where we have the term, new term capital W of I, and then we have the small w of I transpose. The quadratic discriminant function is capable of creating much more complicated shapes, decision planes. Here I have example of just one uh, simple example where we have two intersecting planes that separate the two hyperspheres, orange for carrot and purple for turnip. If you check out the book, there are some much more involved shapes, and uh, so with quadratic function, we have that additional flexibility to classify more complicated data set. That was it for this video. I hope in this and previous videos about Bayesian decision theory, you got an intuition about how Bayesian decision theory works, the intuition behind what is posterior, likelihood, priors, and how all that relates to creating a discriminant function that can be used either in linear discriminant analysis or quadratic discriminant analysis, that we'll see in next video using Scikit-learn and Python. Until then, please like, share, and subscribe. I hope to see you in next video. Thank you.